spectroscopy of ethers. Okay, we discussed last time ethers are this functional group ROR. And what do you mean by IR spectroscopy? IR spectroscopy tell us about the important functional group present in a compound. Main purpose of IR spectroscopy provide information about functional group present in a compound. Important functional groups like carbon-carbon triple bond. This functional group is appear in the range of 2100 to 2300 centimeter inverse in the IR spectroscopy. Carbonyl group, C double bond O group. This group is appear in the range of 1680 to 1750 centimeter inverse. So similarly, ethers can also be appear in the IR spectrum, and IR spectrum is divided into two regions. One region is fingerprint region, and the other region is functional group region. All the important functional group lies in the functional group region. So the ethers contain carbon-oxygen linkage. So the stretching frequency of carbon-oxygen stretch is appear in the fingerprint region, which is appear 1000 to 1200 centimeter inverse. If you remember, the IR spectroscopy is divided into two regions, from 400 centimeter inverse to 1400 centimeter inverse. This region is called fingerprint region. And from 400 to 1400 to 4000 centimeter inverse, this region is called functional group region. So the carbonyl stretching frequency, the carbon-oxygen stretching frequency of ethers appear in the range of 1000 to 1200 centimeter inverse in this region, and this region lies in the fingerprint region. So many compounds have carbon-oxygen stretch. In the IR spectrum, if the IR spectrum has the carbon-oxygen stretch, means if you are seeing a peak in the range of 1000 to 1200 centimeter inverse, but you don't have a peak of carbonyl group. The peak of carbonyl group, I told you earlier, it will appear in the range of 1680 to 1750 centimeter inverse. And if you don't have a peak of OH stretch, can you tell me where this OH peak appear in the IR spectrum?
It would be near 330. Where was it?
Yes, 330. Almost.
Yeah.
OH, yes, excellent. OH stretches appear in the IR in the range of 3600 centimeter inverse to 3200 centimeter inverse. And normally this peak is appear broad peak. You will get a broad peak of OH stretch in the IR spectrum. So in two cases, you will get a broad peak in IR spectrum. One case is if you have OH group, OH stretch of alcohol. And second is if you have OH stretch of carboxylic acid, then you also get a broad peak in the IR spectrum. This OH stretch of carboxylic acid, it will appear in the range of 3100 centimeter inverse to 2500 centimeter inverse. So if you don't have a peak of carbonyl group, if you don't have a peak of OH stretch, then it is confirmed that the compound contains carbon-oxygen stretch at 1000 to 1200. So if both of these peak, carbonyl peak and OH peak are absent, then and you are getting a peak in the range of 1000 to 1200 centimeter, then it is a clear indication that compound contain carbon-oxygen single bond, which is known as ethers. Got it?
Got it.
Okay, perfect. Okay, next one is mass spectrometry of ethers. Mass spectrometry of ether. In mass spectro, can you tell me what is the importance of mass spectrometry?
It can give you the molecular weight of the compound.
Molecular weight of the compound, excellent. And any other information other than molecular weight?
Common fragmentations.
Excellent. Possible fragmentation. The two main advantages tell us the molecular weight, and you can calculate the molecular weight by using carbon rule of 30. And secondly, it will provide you fragmentation of the unknown compound. So this is your ethers. This functional group is ether. So ethers, in ether, mostly alpha cleavage is going to take place. What is alpha cleavage? This oxygen, the carbon next to oxygen, this carbon is called alpha carbon. So in alpha cleavage, we are breaking this bond, alpha cleavage between the alpha carbon bond. So if I am breaking this bond from here, what will happen? This radical is going to form, this alkyl radical, which is not observed in the mass spectrum, while the other fragment, which is the dominant fragment, which is formed, which is known as oxonium ion, this ion. If I am cutting this bond, then this oxygen deficiency of bond, it will carry a positive charge. So this positive charge is compensated by the lone pair of electron, and as a result, oxygen carry positive charge. So this species, a species in which oxygen carry a positive charge, is known as oxonium ion. This is a stable fragment which appear in the mass spectrum of these ethers. So main fragmentation is the alpha cleavage to form resonance stabilized oxonium ion. This is a resonance stabilized. If a compound having resonance, if a compound is stable, if the fragment is stable, then its intensity is high. And if normally it will be a base peak in the mass spectrum. So ether alkyl group can be cleaved in this way. We can cleave this alkyl group as well. So let's discuss the cleavage of alkyl group. The dominant cleavage is alpha cleavage in case of ethers. You can also break down this alkyl group. So loss of an alkyl group, this is alkyl group. If I am breaking this alkyl group from here, what will happen? Again, I am getting an oxonium ion. Okay. How this cleavage is going to take place? Whenever we are putting alcohol at 70, providing energy of 70 electron volt, then what will happen? If this is your ether, or CH2 oxygen, or oxygen having lone pair of electron, if I am applying 70 electron volt of energy to this ether, what will happen? One of the electron will be lost by this compound. And as a result, we will get this fragment, this molecular cation peak, or CH2 oxygen. One electron is lost by this oxygen. As a result, positive charge is formed, and this fragment. This is a molecular ion peak, the first peak. Okay. In the next step, what we are doing, how you can draw the mechanism of this reaction. I am writing one hydrogen over here like this. Okay. So what will happen? Now I am this. How many electron a bond can contain?
The carbon bond can have 4.
No. How many electron one bond have how many electron?
2.
So there is a 2 bond over here between carbon and hydrogen. 2 electrons over here. So if I am doing homolytic cleavage, I am shifting 1 electron on this alkyl. It will convert into alkyl radical, this fragment, while I am shifting this radical from here to here. While this radical from here to here. So between carbon oxygen double bond is formed. What will happen? This is R, this is CH. Now carbon oxygen double bond is formed, and this oxygen still has a lone pair of electron, positive charge, this one, and this hydrogen radical is formed over here. So this hydrogen radical will combine with this radical, this one and this one, to make a bond, and as a result, you will get this fragment RCH double bond oxygen H, and now oxygen carry positive charge. You will get this fragment.
So when we're splitting it, right, we're doing it by the alpha cleavage, carbon, right? Alpha cleavage, right? How do I know which one, where I would split it, right?
Okay.
Like, you said it would be alpha cleavage, but
okay, hold on. An example is coming in the next slide. We will discuss this example, and I will go through your question as well there. So next one is, so carbon oxygen can be cleaved to produce carbocation. Okay, here is the example we will discuss. So here is the mass spectra of diethyl ether.
Mhm.
So this is diethyl ether, this functional group diethyl CH3 CH2O into CH2 CH3. This compound is called diethyl ether. Okay, what? So peak which is appearing at 74, this peak is called?
Oh, that's a base peak?
No.
No,
The
it's
first peak,
the, I
molecular
have
ion
this right
peak,
now.
molecular ion peak.
Molecular ion peak. Okay.
Yes, the first peak. And this peak is giving information about the molecular weight of this unknown compound. Okay. So it means the molecular weight of this unknown compound, which is diethyl ether, is 74.
74.
Okay.
Okay. Mhm.
And secondly, this peak is called base peak.
Okay.
The intensity of base peak is maximum, mostly 100. Its abundance is 100 because this peak, this fragment is stable. Okay. So this is
Okay.
base peak. This is base peak. So again, we are applying 70 electron volt to this diethyl ether. As a result, we will get this molecular ion peak, which is appear at M/74. First of all, we are doing ethyl, loss of an ethyl group. So on both sides, now this compound is symmetrical, this one and this one, on both sides. So if I am doing loss of alkyl group, loss of alkyl or loss of ethyl group, I am cleaving this bond. Again, you are getting oxonium ion, and the M/Z value of this fragment is 45, and loss of 29 is taking place. This fragment will not appear in the mass spectrum. So this fragment is detecting, which appear 45. So this is the fragment. Okay, if I am performing alpha cleavage of this compound, oxygen, this is alpha carbon, this is alpha carbon. Now the compound is symmetrical. So if I am breaking this bond, carbon-carbon bond, what will happen? I am getting oxonium ion. The M/Z value is again 59, and loss of methyl group will take place. So loss of 15, M/Z 74 minus 15. So this fragment will appear 59. This is the fragment. And last one is alpha cleavage combined with loss of ethylene molecule. So this fragment, which is found in the alpha cleavage,
Mhm.
sorry, in this fragment, let me write this one, CH3, CH2H. Here is CH2, and here is oxygen double bond CH2. So what is happening over here? Then this oxygen carry a positive charge. This fragment which is formed, M/Z 59. Ethylene molecule is going to release from this fragment. Ethylene molecule is going to release. And how this cleavage is going to take place? Shift this bond over here and this bond over here. And as a result, you will get this fragment which is appearing at M/Z 31, and which is your base peak.
Okay.
Okay. So your
Okay.
question was, if we have like unsymmetrical ether, CH3,
You're right.
O, CH2, CH3. Okay. Okay, let me make it. Okay, CH2, make it like this. Okay, hold on. CH2, CH2, CH3. So this is unsymmetrical ether, right?
Mm-hmm.
So you can do alpha cleavage. You can break this bond first of all. This is alpha cleavage. You can also break this bond. So if the ether is unsymmetrical, you can do alpha cleavage on both sides.
Okay.
Okay, got it?
Yes, the name of this compound, right? This
Yes.
is the ethyl group, and then this is a propyl group, right?
Yes.
So it would be ethyl propyl ether.
Excellent. Ethyl propyl ether. Alphabetically, E comes first and P comes later. So ethyl propyl ether. Excellent. Okay. Next one is NMR spectroscopy. NMR spectroscopy provide information about carbon, hydrogen framework in a compound, how carbon is connected with hydrogen, a carbon is connected with how many hydrogen, and the neighbor, the environment of carbon, how many, like with the help of NMR spectroscopy, this NMR spectroscopy is also helpful in providing the carbon-carbon framework, carbon-hydrogen framework. Like carbon is connected with one hydrogen, carbon is connected with two hydrogen, carbon is connected with three hydrogen, or carbon is not connected with any hydrogen. So with the help of this technique in the mass spectroscopy, this is a perfect technique, most important technique to elucidate the structure of a known compound. And in case of ethers, if we are studying about proton NMR, so this proton, this hydrogen, which is connecting with this carbon, and the hybridization of this carbon is?
sp3.
Excellent, sp3. If the hydrogen is connected with sp3 carbon and sp3 carbon is connecting with oxygen, so this proton, this hydrogen will appear at 3.5 to 4 ppm. Why this proton is de-shielded? Because this oxygen having high electron negativity, it will withdraw electron density from carbon, means it is also withdrawing electron density from the hydrogen. If the electron density on hydrogen is decreases, then the proton become de-shielded, it will appear at higher chemical shift. So the typical chemical shift for NMR, so hydrogen, carbon, oxygen single bond appear in the range of 3.5 to 4 ppm in the NMR spectroscopy, while this carbon which is directly connected with heteroatom, so this carbon will appear in carbon-13 NMR spectroscopy in the range of 65 ppm to 90 ppm. Got it?
Okay.
Okay. Now, very important question. Williamson ether synthesis. Very important reaction. This reaction is completed in two steps. So the first step, if we have any alcohol, ROH, not aromatic alcohol, aliphatic alcohol, I'm talking about aliphatic alcohol. If I am reacting this alcohol either with sodium, or I can use potassium, or I can use sodium hydride. What will happen? This hydrogen is going to remove, and I will get this compound, oxygen carry negative charge. This compound is called alk oxide. Okay. And in the second step of the mechanism, this alk oxide will react with alkyl halide. What is alkyl halide? Rx. This functional group is called alkyl halide. This R could be anything. It could be methyl, ethyl, propyl, butyl, any alkyl group. While this X could be halogens, and halogens include fluorine, chlorine, bromine, and iodine. So this functional group is called alkyl halide. And I hope you have studied about classification of alkyl halide, like primary alkyl halide, secondary alkyl halide, and tertiary alkyl halide. Can you tell me which alkyl halide is this?
Okay. It's connected to 3 points, so it's tertiary. Secondary
alkyl halide.
Because
why secondary alkyl halide? Because the halogen is connecting with carbon. This carbon, it is directly connected with two carbon. One carbon this side and one carbon this side. Okay.
Yeah.
So this is secondary alkyl halide, not tertiary alkyl halide. Okay. And what about this one?
Primary
alkyl halide. Excellent. And what about this one?
That one's tertiary.
Yes, that's tertiary alkyl halide. Excellent. The most important point about the second step of synthesis of ether is that you can use either primary alkyl halide, you can use either secondary alkyl halide. You can't use tertiary alkyl halide in the synthesis of ether using Williamson method. Okay? That's the most important. You can use primary alkyl halide, you can use secondary alkyl halide. So I am explaining the general mechanism. I am writing Rx. So what will happen?
Okay.
This oxygen carry a negative charge. It will attack on this alkyl group, and this leaving group will leave. As a result, you will get this functional group ROR. This functional group is called ether, and this halogen will leave. Got it?
Okay. So we make the alkoxide if it's a hydrogen, right?
Yes.
And then
Alcohol, we convert alcohol first of all, aliphatic alcohol, aliphatic alcohol. So we will convert alcohol into alkoxide. You can use sodium, you can use potassium, or you can use sodium hydride. And in the second step, you are reacting your alkoxide with alkyl halide. And the alkyl halide, which you can use primary or secondary, you can't use tertiary alkyl halide.
okay.
Got it?
Got
And
it.
you can't, and you also can't use you can't use hindered primary alkyl halide as well. Hindered primary alkyl halide, like you can't use this alkyl halide in the synthesis of you can't use this alkyl halide in the synthesis. Which alkyl halide is this?
One second. 1, 2, 3, 4, 5.
Which alkyl halide? Primary, secondary, or tertiary?
Oh, I thought you were asking me to name it. Sorry, it's primary. This is directly connected to one other carbon.
Sorry?
It's directly connected to one other
Yes,
carbon.
one carbon. Bromine is connected with this carbon, is connected with one carbon. So this is primary alkyl halide. Although this is a primary alkyl halide, but still it does not give you ethers. Why? Because this primary alkyl halide is sterically hindered. These bulky group would not allow this alkoxide to attack, to approach on this carbon. They will create steric hindrance. Okay. So the alkyl halide, you can use primary and secondary, but you have to use unhindered primary alkyl halide. If you are using hindered alkyl halide, then this reaction will not take place. You will not get ether. Instead of ether, you will get alkene. Elimination will take place instead of substitution. Got it?
If it looks complicated like this, if it looks like it's sterically hindered, that's what it's called.
Yes,
right?
sterically.
Then we cannot use it.
Sorry?
Then we cannot use it.
Yes, you cannot use this compound for the synthesis of ethers.
Okay.
Okay. So, and have you learned about SN2 reaction?
We have.
SN2 reaction stands for SN2 reaction stands for
substitution and it's not numerical.
Two stand for bimolecular nucleophilic substitution reaction. The reaction in which bond formation and bond breakage take place in a single step, and always the incoming nucleophile attack from the opposite side of the leaving group, always. And inversion of configuration take place in SN2 reaction. I hope you have learned SN2 reaction in detail. So in the second step, when alkoxide is going to attack on this alkyl group, it will attack from the opposite side of this leaving group always. So here the substitution reaction which is going to take place is SN2 reaction.
Backside attack.
Okay.
Right. That's what we called it in class, backside attack.
Yes. So let me move forward now quickly. We discussed all the import. Okay, we can use tosylate as well. Primary alkyl halide in the second step. And we can also use tosylate as well. Tosylate is a very good living group. Sorry?
OTS, right? That's what it looks like, OTS.
OTS, yes. OTS. Yes, OTS. Excellent, OTS. Paratoluene sulfonyl chloride, OTS. So here is the examples are given. This is alcohol reacting with sodium. It will give you this alkoxide. And the next step, this alkoxide will attack on this carbon because OTS is a good living group. OTS is a very good living group. And in SN2 reaction, if you remember, we used good living group. So this group will leave over here and you will get this compound, and this functional group COC This is called ether. And the yield of this reaction is 92%. And this is called ethoxycyclohexane. Again, if I'm reacting this compound, alcohol with sodium hydride is a strong base. Strong base, sodium carry positive charge, hydrogen carry negative charge. So this negative charge will attack on this hydrogen. And this bond will shift on oxygen. So you will get alkoxide first. You will get this alkoxide. So this alkoxide will attack on this methyl and iodine will leave via SN2 reaction. And you will get this compound, this ether will form as a result. And what's the name of this ether? We will start numbering from this side. 1, 2, 3, 4, 5. So methoxy is present on carbon number 2. So 2-methoxy, 3,3-dimethyl pentane is the name of this compound.
Okay.
Next one is phenyl ether. Okay. How we can synthesize phenyl ether? So if you have alcohol, and this compound is called 2-nitrophenol. If I'm reacting 2-nitrophenol with sodium hydroxide, what will happen? So first of all, this hydrogen is going to leave. You will get tosylate. You will get alkoxide, phenoxide. This is called specifically phenoxide.
Mm-hmm.
And in the second step, this phenoxide will attack on this primary alkyl halide. This is unhindered primary alkyl halide. And this group will leave and you will get this compound. So phenoxide ion are easily produced because the alcohol proton is acidic. Why they can easily produce? Because this hydrogen is acidic. Why this hydrogen is acidic?
Because it has an alcohol in it?
Like,
because it has resonance. Because it has resonance. Sorry. Because it has resonance.
Yes, it has resonance. It has resonance.
And because it has resonance, it's more stable.
Because the conjugate base is more stable after losing hydrogen. The conjugate base is stable. If the conjugate base is stable, then the acid is strong. Okay. So phenoxide ion are easily produced because the alcohol proton is acidic. So this base can easily convert this phenol into phenoxide. Phenyl halides or tosylate can't be used in the synthesis method. In the second step, you can't use phenyl halide. You can't use this halide over here. You can't use phenyl tosylate as well. Benzene, and it is attached with OTS. You can't use. Why? Because this alkoxide cannot attack on this sp2 hybridized carbon. It always attack on sp3 hybridized carbon.
Okay.
Got it? So if professor give you any alkyl halide like this one, in the second step, then no need to carry out the reaction. Simply write no reaction.
Okay.
Got it?
Got it.
Okay. 1 second. Solve example. How now the answer of the problem which we discussed earlier. Why is the following reaction or is a poor method for the synthesis of tertiary butyl propyl ether? Why this method is poor? Because, okay, what would be the major product of this reaction? Propose a better synthesis of tertiary butyl propyl ether. So this is sodium phenoxide. If I am reacting this compound, which alkyl halide is this?
This is a tertiary.
And I told you tertiary alkyl halide don't give you Williamson ether synthesis. You can't synthesize. Okay, sorry. Okay. You can't synthesize ethers using tertiary alkyl halide. So you will not get this compound. Then what's the solution? The desired SN2 reaction cannot occur on tertiary alkyl halide. Alkoxide is a strong base as well as a nucleophile. The elimination prevails. So this sodium phenoxide, this is a very strong sodium propoxide. This is a very strong base. If the base is strong, then elimination reaction will take place, and particularly the reaction which take place is E2 elimination. Okay, if base is strong, then base always abstract beta hydrogen. So this is bromine. This carbon is called alpha carbon, And this carbon is called beta carbon. Hydrogen
Okay.
connected to beta carbon is known as beta hydrogen. So this phenoxide ion will attack on this beta hydrogen. This bond will shift over here, and this bromine is going to leave. You will get this alkene as a product. So instead of getting ether, you will get alkene if you are using tertiary alkyl halide.
It's asking how the question is asking for a better synthesis of.
Yes, we will discuss soon. Don't worry.
Okay. Okay.
Here is the better synthesis. So the better synthesis is, instead of using propoxide, why we can't use this sodium tertiary butoxide? Like if I'm using this compound, this alcohol, tertiary butyl alcohol, if I'm earlier I used this alcohol, propyl alcohol. In the previous method, we use propyl alcohol. We react this propyl alcohol with sodium hydride, and we generated propoxide. Now, if I'm using this tertiary butyl alcohol reacting with sodium hydride, then I will get this sodium tertiary butoxide. So in the second step, if I am reacting this sodium tertiary butoxide with primary alkyl halide, this will attack on this carbon, this will leave. So as a result, you will get your tertiary butyl propyl ether. So this is a better synthesis because you are using an unhindered primary alkyl halide in this reaction. So no chances of elimination, only substitution will take place. And the substitution which is take place via SN2 reaction.
Okay.
Got it?
I think I got it.
Perfect. If you got this one, write the product of this reaction. If you are reacting this compound with this reagent, and in the second step, if you are reacting this compound this is benzene ring.
Mm-hmm.
Yes. What's the product?
This is primary. This isn't hindered, right? This goes away. This is an alkoxide method. So it goes to
You don't have pen tablet?
No, it's okay, bro.
Okay.
It adds here. This goes away. So it goes here. I'm just using my finger. It's not the best.
Is this reaction can take place? Which alkyl halide is this?
This is a primary, right?
Yes, this is primary. Is this primary alkyl halide hindered or unhindered?
I thought it, because this point didn't look hindered to me.
Sorry?
That looks unhindered. This
No.
part looks unhindered.
How it can look unhindered? This phenyl ring will not allow easily to approach this alkoxide from either of the side. This is a very bulky group. Okay. And this methyl is also on the bottom side. It will not allow this oxygen to approach on this carbon, on this primary carbon. Okay. So you will get only alkoxide. You will not get your final product. Okay.
And I'll do hindrance problems later. Stereochemistry.
Yes, stereochemistry.
Okay.
Okay, next one is next synthesis. Next method to synthesize ethers is alkoxy demercuration and demercuration reaction. And I hope you have learned about mercuration, demercuration of alkene. If you remember mercuration and demercuration of alkene, this is alkene CH2, CH2, CH, okay, let me write this way. CH3, CH double bond, CH2. If I am doing mercuration, demercuration of this alkene using, you can use water molecule. I'm using water molecule in the second step, and using sodium borohydride as well, NaBH4. So 3 important points about mercuration, demercuration. The first important points, it follow Markovnikov rule. Markovnikov rule. Do you remember Markovnikov rule?
We had a saying, the more it is, the better or something. 1 second, I have it written down.
Okay.
I have it written down.
Okay.
I have all the important things written down.
Okay. Take your time, then I will explain to you.
Thank you.
Okay.
Is it in this folder? Is it in that old folder? Is it in that old folder? Okay.
Yes, carry on.
I'm gonna get it.
Okay. What this Markovnikov rule says, what's the statement of this Markovnikov rule? Rich become richer or poor become poorer?
Rich becomes richer.
Yes, you can say the okay. What's you find out about Markovnikov rule?
The rich get richer.
The rich get richer. For example, okay, let me explain. If you have this compound, this alkene, CH3, CH double bond, CH2. If I am reacting this alkene, unsymmetrical alkene with HBr, hydrogen carry partial positive charge, bromine carry partial negative charge because the electronegativity of bromine is higher as compared to hydrogen. So according to Markovnikov rule, if we are adding unsymmetrical reagent to unsymmetrical alkene, then the positive part of adding reagent goes to that carbon of double bond which contain more hydrogen. Means this hydrogen become richer. Earlier it contained 2 hydrogen, this carbon contain 1 hydrogen. So this hydrogen will prefer to go to the carbon which is more rich.
The bond will shift, so it will be CH3, CH2, CH3.
Okay. Yes, CH3, and this carbon will carry a positive charge, and in the next step, what will happen? This bromide will attack on this carbon.
Okay.
So what's the product? CH3, CH, this is Br, and this is CH3. Rich become richer. This carbon contain 2 hydrogen, this carbon contain 1 hydrogen. So hydrogen prefer to go to that carbon of double bond which contain more hydrogen. This rule is known as Markovnikov rule. So oxymercuration, demercuration, first of all, follow Markovnikov rule. Second important point about oxymercuration, demercuration, no carbocation rearrangement take place. No carbocation.
Sorry? An anti-mark it does, right?
No.